this is a good time to start. I want to go back and look at an experiment that was historical, and unfortunately, you remember this experiment as not being as being revolutionary, because I was getting interested in this topic about that time. And it happened, it's an experiment that was published in 1975. What were your parents born?
63.
Yeah, I'm little, they would have been born by that time. Günther Lobel and Doberstein published a paper that actually revealed how secretory proteins are made. And their work was awarded in 1999 with the Nobel Prize in Medicine. It was really an important discovery. So I looked at the paper, I came and looked at the paper this morning to get a clue as how much is this am I making up? And I'm actually not making it up. So I thought I was just throwing these different control conditions and experimental conditions in just for the heck of it, but I'm not. This is actually the experiment that they did. And then I will throw in one other condition and have you anticipate what would that have, how that would work. So they had isolated, which is amazing, the messenger RNA. Now, given 1975, I think this is amazing for the light chain, and I think it's like the IgM light chain. Okay, so this is a protein that would become a luminal protein of the ER, okay, a luminal protein of the ER, and then it would eventually get secreted, but it doesn't float off because this is the antibody, and this is outside the cell, this is inside the cell, okay? The light chains are disulfide bonded to the transmembrane domain. So these are essentially integral membrane proteins, but they're really not. They're secreted, but they can't float off because they're covalently linked to the membrane-bound heavy chain of the antibody. Okay. So what Lobel and Doberstein did was put the messenger RNA into a cell-free protein synthesis system, which you can buy. You can buy cell-free protein synthesis systems, or you can make your own. Okay, and it requires a messenger RNA. Okay, and they had a messenger RNA. Requires some ribosomes. It requires some amino acids. Okay. And back in 1975, one of the amino acids was radioactive. I don't think we would do that today. Maybe. I'd rather not do that today. And let's see, what else do we need? An energy source, which is kind of interesting in itself. So those are the things you needed. Like I said, you could buy these cell-free protein synthesis assay kits, and all you have to do is add your messenger RNA, or you could make your own. And they, at that time, probably made their own. Okay? They also isolated endoplasmic reticulum. Okay, an endoplasmic reticulum in the cell is this great, big, huge membrane system. Sometimes I wonder how many endoplasmic reticulums you actually have in the cell. Maybe it's just one great, big, giant one that happens to just be like a channel, giant lake system. Okay, but when you're isolating these from the cell, something this big and this narrow and this kind of networky like is going to fall apart, okay, it's going to disintegrate, and what's going to happen is, because you have to completely bury the hydrophobic fatty acids, you end up with smaller kind of lithosome things, okay, smaller chunks or fragments of ER, and these are called microsomes. Okay, and I don't know if they could at that time control for, how do you know if the microsome is inside out or outside right, you know, it has the right orientation or the wrong orientation? Because you could have, make an inside out microsome, which would be a kind of a bone. Okay, so they needed microsomes, and they needed the cell-free protein synthesis assay. Okay, so here's how the experiment went. And I am going to draw, can I erase all of this? Is that okay? You got it? Draw a very big electrophoresis gel. Sample 1, sample 2, sample 3, 4, and then you're going to anticipate what 5 might look like. 5, okay. So you could put samples, different samples in wells and electrophoresis the proteins downward, or the large proteins are going to migrate more slowly through the gel because they are large, and large things diffuse more slowly than small things. Small proteins are going to move a little faster because molecules that are smaller do move faster. Okay, so the control, I'm going to just say store-bought small chain. It probably wasn't store-bought, they probably isolated it, but today you would just go to the store and just order something that was already purified, and you would throw it on your gel so you know exactly where does this protein band out in the gel. So we're going to put it here. Okay, so this protein would show up on the gel, let's just say there. And this was a mature light chain. Okay, so that's what okay, so then they had a bunch of experimental conditions. Okay, one was they just threw the messenger RNA into a cell-free system and let translation take place on the ribosomes. Okay, so cell-free protein synthesis system. Okay, cell-free protein synthesis system. And then afterwards, they electrophoresis the proteins that were made by the cell-free protein synthesis system, and they realized and they recognized that the light chain seemed to be what? Bigger or smaller? Bigger. Okay? So that's what the messenger RNA made. Then they did another setup. Where they did the exact same experiment, but they did it in the presence of microsomes. Okay? So everything was present. And this time they threw in the microsomes that they had isolated. Okay, so they let the proteins get made, they incubated them for a while, the proteins were synthesized, they electrophoresed the proteins, and they got this. Okay? So the protein that was made in the presence of the microsome is a No, I was right. No, that's gonna be one of these days. Sorry, you're right. I don't know why I had a brain fart. Okay. It's in my nose right. Sorry. If you're anal like me, I just screwed up your nose. Okay, so in the presence of microsomes, what happens to the protein? It gets shorter. And now it's the same size as the mature light chain antibody. Okay, so without the microsomes, you make a longer protein. With the microsomes, you make a shorter protein. Okay, let me do this one. So that's 2. Okay, so in 3, lane 3, they first added the messenger RNA and the protein, cell-free protein synthesis system. Okay, and then they incubated so that the proteins could be made. So this is first an incubation. Okay, proteins were synthesized. After synthesis, okay, microsomes were added after synthesis. So microsomes were added later. Incubated a little bit more. Okay. And this became number 3. Okay, I need this. I'm not going to change it. And what they saw was a bigger protein. Well, this was a huge clue. If you add the microsomes after protein synthesis has been completed, they're not going to shorten the protein. They're going to keep the protein at the same length. It's kind of odd. Okay, here's another, this is another experiment. So this was number 2. After they did number 2, okay, recreated experiment number 2, where they did messenger RNA, the cell-free protein synthesis system, and the microsomes. Let it incubate, and they added then a protease. Okay, and that's going to be number 4. Okay, they added a protease.
Did they add the protease like after the synthesis?
Yeah, right. They added the protease. They first incubated with this compaction, the messenger RNA protein synthesis system and the microsomes together. Let protein synthesis take place. Then they added protease to chop up proteins. So what do you suppose they found? They found fat. What do you suppose this means about the protein and its location? Apparently this protein was protected from proteases. How could it be protected from proteases? Where would be the best place to be, okay, to be protected from the protease? How about inside the microsome? Okay, so the addition of protease showed that it's not breaking down the light chain antibody. So the light chain antibody has to be somehow protected. And the only way you could protect the antibody, the light chain antibody at this point is have it be inside the microsomes where the proteases can't get to the light chain antibody. Okay, because proteins cannot cross a cell membrane or any kind of membrane, even an ER membrane. Okay, so that was an important experiment. Aha! Not only do we see the protein becoming shorter, it's also becoming, it's also protected. Okay? And then they did this one where, okay, this experiment. Okay, protein synthesis system, incubate. Add the microsomes. Incubate. Okay, and you get lane number 3. Let's add protease to that, okay? So we're recreating this experiment where we added the messenger RNA in the protein synthesis system. We let protein synthesis take place. Then we added the microsomes. Let that incubate for a while. Then we added the protease to see where and that the question is, where is the protein located? What do you expect they saw?
All the way in the bottom. All the way in the bottom.
They saw a mess. Okay, well, it wouldn't have gone down past. The protein was destroyed. So where was the protein in this case? It was outside. It didn't get into the microsomes. It was outside the microsomes, and the protease degraded the light chain antibody because it wasn't protected by the microsome membranes. So what can you tell me about the synthesis of a secretory protein like the light chain antibody?
Finishes in the ER.
Yeah, it has to get in first, it has to get into the ER. What's going to happen to it in the ER? It's going to get clipped so that it's a slightly smaller protein. Okay? Does the insertion into the ER require concurrent protein synthesis, or can you add it to the ER later on? It has to be inserted into, it's only inserted into the microsomes or ER while protein synthesis is taking place. So I remember that there was a a big word that everybody back in the late 70s, early 80s just had to memorize. Co-translational translocation. Okay, so the movement into the ER required translation taking place. Okay, so the two events were simultaneous. Okay, proteins are transferred into the endoplasmic reticulum during protein synthesis. We now know that there are some exceptions to that rule. You can do post-translational translocation, but almost all of our proteins are moved into the ER by co-translational translocation. So that was the big word. Other people then proved that, oh, this is also true with proteins that end up on the plasma membrane. So that was the follow-up experiment by Harvey Lotish, who is the author of the other cell textbook. Okay, so today we're going to take a look at what is this all about? How do you do co-translational translocation? Okay, but I do want to spend time before we do that looking at what is it that gets cut off the protein.
Is that experiment in the book?
It is. It is in the book. I used a different book though.
Okay.
But I saw that bits and pieces of this experiment is in the book. There's another book that has actually the real photograph of the gels. Okay, and our textbook cleans up those real gels by just drawing pictures like I did. So that's a cleaned up version. So the signal sequence is the thing that gets cut off. Okay, its primary purpose for being on a protein is to get that protein to be made in the ER. And once the protein begins its movement into the ER, don't need it anymore. And it looks like this. The book has a sample signal sequence, but it doesn't fit the standard pattern of a signal sequence. Okay, so always, amino acid number 1 is methionine. And somewhere close to somewhere inside there is going to be a positively charged amino acid, usually arginine or lysine. Okay. And your book doesn't show that. There's a table at the beginning of chapter 12 that looks at different address labels. And they show a signal sequence, but they don't show one with a positively charged amino acid. But I've seen signal sequences, they have a positively charged amino acid. Then there's going to be about 6 to 12, okay? Yeah, very hydrophobic amino acids. Any different for a while. And then there's 2 amino acids that make up a cleavage site. Okay? So this is the N-terminal amino acid sequence, and inside of the ER signal sequence gets cut off. And so this cleavage site then becomes the new N-terminus, okay? So you lose, I don't know, 20 or 25 amino acids from the protein. And so that's why it's able to, that's why we see a change in size. And because this enzymatic activity is inside the ER, you gotta get the protein into the ER in order to get the signal sequence cleaved off. The signal sequence will be degraded. Okay, it's just gonna end up becoming degraded. Okay? This happens during protein synthesis. This removal happens during protein synthesis. And the name of the enzyme that does it is signal peptidase. Which is a resident protein of the ER. It happens to be an integral membrane protein of the ER. So by the time the ribosome reaches the stop codon, okay, and finishes protein synthesis, that signal peptide is long gone. So the protein that gets released from the ribosome is a protein without a signal sequence. And that's why it took so long to find signal sequences, because 1975 is actually a pretty late date considering, we knew about protein synthesis for a long, long time. Okay, so that makes sense. We're going to lose the first half. So I'm going to call this, because there's going to be other kinds of signal sequences. This is an N-terminal signal sequence. Okay, at times we might call it a start transfer sequence. Okay, because it's this sequence that directs the ribosome to the endoplasmic reticulum. And that sequence starts the transfer of that protein into the ER. Okay. All N-terminal signal sequences are going to be removed because signal peptidase is going to recognize that as an N-terminal signal sequence and will remove that N-terminal signal sequences. We will also see later on, which will muddy up the pictures, internal signal sequences. And I need to go back and that are also called start transfer sequences. And again, this is going to muddy up the water a little bit. Internal signal sequences never ever get removed. Okay? Only N-terminal signal sequences. And we'll come back to that probably get it for the first time tomorrow. Look at the difference between an N-terminal signal sequence and internal signal sequence. But it's going to be really hard to just hope you understand when I'm saying N-terminal and internal. Okay. So are you ready to look at how this signal sequence works? Okay, we got a half hour. This is get your colors out. Okay. Okay, and so if you want, you're going to need a whole page, okay, with lots and lots of writing on it. I used to hand this out, but I think when you draw it, you draw hand. You do that. Okay, today, and I just learned some quality control stuff, so I got stuff to add today that I've never talked about before. Okay, do you guys remember in a ribosome, there's a P site, A site, actually E site, which I didn't show. Where's the growing peptide located? It's going to be the peptide, the P site, okay? And actually, the P site, not the A site, but the P site, really creates a channel that runs through the entire large ribosomal subunit. The A site is not a channel, but the P site is a channel. So the growing protein, I'll make it yellow. Oh, I'm going to have the signal sequence here. So the signal sequence is going to emerge out that channel on the large ribosomal subunit when the amino acid, when the protein's about 40 amino acids long. So it takes a little bit, that tunnel is rather large, so after about 40 amino acids, then the protein starts poking its way out of the ribosome. And it is an address label, because it's the thing that's going to direct the protein to the ER. So it needs an address reader. Okay, and the address reader, I'm going to draw this. Right? The book draws it differently. Okay, so my big piece of this. This is called SRP for the signal recognition part. Okay. It's a big complex of 6 proteins and an RNA molecule. Okay, so I'm going to draw a quick map of this. The book has it. The book draws it probably more the way it is structured, because there's a hinge in this complex that moves moves. So this mouth kind of moves around a little bit. I'm going to continue to draw it as one shape, but it does. There's a kink to it, a hinge that can open and close. Okay, whoops, wrong piece of paper. Okay, so there.